Okay, next we calculate the determinant of a second matrix. The matrix written out in typewriter notation would have a first row 2, 3, negative 4. There's a semicolon delineating another row. Second row would be 3, negative 2, 4. Another semicolon delineates a third row 1, 1, 1. So the matrix is 2, 3, negative 4, 3, negative 2, 4, 1, 1, 1. Now these circles and everything will become apparent as we move through it. Ignore that for the moment, but we'll get to that very quickly. Okay, so to do the determinant, we start with the first number in the first row, and we eliminate the rest of that row and the rest of that column, and that leaves us the matrix negative 2, 4, 1, 1, the matrix we have here. Again, take the 2, eliminate the row and the column, we're left with this matrix here, which I've written down here. Now, in calculating the determinant, the first calculation we then do is we multiply 2 by the determinant of this matrix. So, the red circle indicates that we're using the 2 and this matrix here, and it's circled again here. And we're multiplying the 2 by the determinant of that matrix. Okay, the next number in the first row is 3. Now what we're going to do then is we're going to subtract 3 times the determinant of this matrix. Now, how do we get this matrix? Well, we again eliminate the row and the column of the 3. That leaves us these two, well, this column of 2, which goes here, and this column, which goes here. So again, eliminating the row and the column of the 3, and I'm probably blocking the row here, or the column here. We have the 3, 1, 4, 1. And that's our matrix here. And we do then minus the 3 times the determinant of that matrix. Then with the third number here, we go back to a plus, we add, but we add this number, which is negative 4, times the determinant of the matrix we get when we eliminate the row and column of the negative 4. And that matrix, of course, is the 3, 1, negative 2, 1. Now I've circled the negative 4 in yellow and this matrix in yellow, just so we can see how everything goes together in case that's necessary for you. Okay. Well, that's straightforward enough. We know how to compute the determinant of the 2 by 2 matrix, so the rest is relatively simple. We take 2 times the determinant of this matrix. The determinant is negative 2 times 1 minus 4 times 1, which is going to give us negative 2 minus 4. So I write that down here as 2 multiplied by the negative 2 we get here from this diagonal and the negative 4 that we get when we subtract this diagonal. Then we're going to have our minus 3 times the determinant of this matrix. We're going to have 3 here minus 4, so we have our 3 minus 4. And then we add negative 4 times the determinant of this matrix, and we have a 2 here and minus a negative 2 here, which is going to give us 3 plus 2. So we have 2 times minus 6, minus 3 times negative 1, minus 4 times 5. Just doing the arithmetic here. And that adds up to negative 12 plus 3 minus 20, which is negative 32 plus 3 is negative 29. So, in summary, to do the determinant of a 3 by 3 matrix, you take the first number in the first row, eliminate the row and column of that number, and take the remaining matrix, and then we're going to take this number multiplied by the determinant of that remaining matrix. Then we do something similar with the second number in the first row, except now we subtract. We have minus 3 times the determinant of the matrix that's left over when we eliminate the row and column of the 3. And then we do plus this one this number, the third number in the first row, multiplied by the determinant of the matrix we get when we eliminate its row and column. The rest of the calculation is very simple and straightforward. You just got to be careful about signs and getting the arithmetic correct. Applying the same rule to this matrix, we have our 2, eliminated the row and the column. We're left with a negative 3, 1, and a 4, 1, negative 3, 1, 4, 1. So we have 2 times the determinant of this 2 by 2 matrix. Then minus this, minus the quantity 1 times the determinant of, eliminate the row and column, we end up with a 3, 1, and a 4, 1. Okay? Then we have our minus 4. We're going to do plus that minus 4 times the determinant of the matrix we get when we eliminate the row and column of the negative 4. That would be the 3, 1, negative 3, 1. The matrix with columns 3, 1, and negative 3, 1. We do the arithmetic, and we end up with negative 27. Now I've got so y equals negative 27 over 29. Ignore that for the moment. We'll relate that to the system in a fairly obvious manner if you understand what we did in the preceding. But then we can do the same here. We've got another determinant to evaluate. Well, it's going to be 2 times the negative 2, 1, negative 3, 1, minus 3 times the determinant of, well, we eliminate this column. We're going to end up with a 3, 1 and a negative 3, 1. And then plus 1 times the determinant of the 3, 1, negative 2, 1 columns. And I haven't, we didn't evaluate that in class. I'll probably do that quickly at the end here. Now, let's see how this relates to the system. The system from which we obtain these matrices is here. The coefficient matrix, the matrix of the coefficients of x, y, and z, is clearly our, well, what are our coefficients? X coefficients are 2, 3, and 1. So 2, 3, 1 in the first column. Y coefficients are 3, negative 2, 1. Here's our 3, negative 2, 1. Z coefficients, negative 4, 4, 1. Negative 4, 4, 1 here. So this is our coefficient matrix for this system. The determinant of the coefficient matrix is negative 29. Now, this matrix, how does this matrix come from the system? Well, what we want to look at, just as before, if we're solving for one of the variables, we're going to replace the coefficients corresponding to that variable by the numbers on the right-hand side, just as we did with the 2 by 2 case. So let's see, which column got replaced by the 1, negative 3, 1? Well, it looks like it's the middle column. This matrix matches this matrix except for the column corresponding to the y values. In other words, the 2, 3, 1 is the same. The negative 4, 4, 1 is the same, but the middle column, the one that corresponds to the y coefficients, is just the coefficients of the right-hand side, and that's over here, the 1, negative 3, 1. That means, if we follow the pattern from before, that our solution for y will be the determinant of this matrix divided by the determinant of the coefficient matrix. And that's negative 27 over negative 29. Now, this matrix giving us the negative 27, this one giving us the negative 29. This matrix here has the 1, negative 3, 1 in the third column, which means that we've replaced the z coefficients. The rest of the matrix is the same as the coefficient matrix. So if we finish calculating all this, we can get our solution for z by dividing the determinant of this matrix by the determinant of this matrix. Whatever we get from this calculation divided by the negative 29 we got from our coefficient matrix. So completing the calculation here, calculation's pretty straightforward. We get negative 2 plus 3 is 1 here for the determinant. 3 and subtracting negative 3 gives us a 6 here. So this determinant is 1, this determinant is 6. This determinant is 3 plus 2 is 5. So we have 1, 6, 5. 2 times 1 is 2. Minus 3 times 6 is negative 18. 2 and negative 18 gives us negative 16. And we add 1 times 5, which is just 5, to negative 16, we get negative 11. That's the value of the determinant. So dividing this determinant by this determinant with coefficient matrices, we get negative 11 over negative 29, which is just 11 over 29. We haven't done the determinant for the x, although that was part of the problem, and that was the one I let people work out themselves in class. People did pretty well with that, better than I'm doing. Losing track of this arithmetic. But the result from the determinant you get if you replace the first column of this matrix with the 1, negative 3, 1 is going to be 19. Okay, the determinant of that matrix will be 19 divided by the negative 29 gives us x value negative 19 over 29. And there's a correction on the y value. I mentioned that, made an arithmetic mistake here. Negative 14, negative 24 is negative 38. As I said, you add 1 and you get negative 37, not negative 27. So that y should be negative 37 over negative 29, or 37 over 29. We can check this. For example, in the third column, we have just x plus y plus z. So that's going to be negative 19 over 29 plus 37 over 29 plus 11 over 29. Well, 37 and 11 is 48. Subtract 19, you get 29. We end up with 29 over 29. So x plus y plus z equals 1. This is pretty good confirmation, but of course we would want to plug in here and here as well to completely check this solution. The method we're illustrating here is called Cramer's rule. Very straightforward rule that can be applied to any system of matrices. Although if the system is much more than 4 equations and 4 unknowns, it gets a little bit impractical to evaluate the determinants. I did mention in class that if you had a determinant with 4 rows and 4 columns, then you would do very much the same thing we did here. You would take the first number in the first row, eliminate that row and column. That would leave you another determinant, but that would be a 3 by 3 determinant, 3 rows and 3 columns. And the 3 by 3 determinant would have to be evaluated just the way we evaluated this one. In other words, you'd have a couple more steps to go. Then you would have to go to the second number in the first column and do the same thing. So you'd have another 3 by 3 determinant to evaluate. And then you'd have a third and a fourth number in the first row. And you would do the same. You would get 2 more 3 by 3 matrices to evaluate. So you'd end up evaluating 4 3 by 3 matrices to do a 4 by 4 matrix. And each 3 by 3 matrix would have to follow the procedure that we use here. Now that would be manageable. If you went to 5 by 5, you would end up with 5 4 by 4s, and each of the 4 by 4s would require that you evaluate 3 3 by 3s, and each 3 by 3 requires that you evaluate 3 2 by 2s. So you see that the numbers mount, and by the time you get up to a 10 by 10 matrix, 10 rows and 10 columns, you'd have over 3 million 2 by 2 matrices to evaluate, and that's obviously impractical. The row reduction strategies that we learned earlier are much more practical for larger matrices. But for a 3 by 3 matrix, this is quite a practical way to do the calculations.